In 1908, archaeologists digging in Crete found something unexpected: a solid lump of purple dye, preserved for 4,000 years. When they cracked it open, the inside was still brilliant, vibrant purple. That dye came from the mucus of the murex snail. It took 10,000 snails to produce a single gram. The purple was worth more than gold, reserved for emperors and the most sacred textiles. But the real wonder is its permanence. The color comes from a molecule called 6,6-dibromoindigo, a close chemical relative of the indigo in your blue genes. Two bromine atoms lock the molecule into a stable configuration that resists sunlight, air, and millennia. That is why a 4,000-year-old lump still looks purple on the inside. This is not merely a historical curiosity. It is evidence that our ancestors possessed deep chemical knowledge without microscopes or modern chemistry. They understood how to control molecular structure to achieve permanent color. This level of control required precise knowledge of chemistry, even if they did not call it that. If they could make colors that last 4,000 years, what else did they know, and how can we learn from them today? How did they discover such a complex process? The process involved harvesting the snails, extracting a tiny gland, then fermenting it in sunlight and air for days. How did anyone first figure out that sequence? It seems almost impossible without centuries of accumulated knowledge, and this is not an isolated example. Across the ancient world, dyers created colors that outlasted empires: reds, blues, yellows, all chemically stable for centuries. In China and Peru, dyers independently developed similar methods. Their knowledge was not accidental. It was built on centuries of observation and experiment, passed down through generations. It was a practical science, refined over generations through trial, observation, and trade. The story of these unfading dyes challenges our linear view of progress and offers lessons for a more sustainable relationship with color. To understand how it all works, we need to go inside the dye vats and follow the ancient trade routes. Trade routes spread not only the dyes but also the chemical knowledge behind them. That is what we will explore. Let us start with the most famous of them all, Tyrian purple. On the southern coast of Peru, the Paracas culture wrapped their deceased in intricately embroidered textiles around 2,000 years ago. When archaeologists uncovered them, the colors were still striking: deep indigos, vivid reds, bright yellows. The blues came from indigo, the same molecule used in Egyptian mummies and Chinese silks. The reds came from a plant source, likely a relative of madder, bound to the fibers with a metallic mordant. These textiles were preserved in dry desert conditions, but the chemical stability of the dyes played the crucial role in their survival. Similar chemical stability appears in Egyptian mummy wrappings from the Ptolemaic period, which still show traces of bright madder red. Madder relies on a molecule called alizarin, which forms strong bonds with aluminum or calcium ions, creating a color lake that resists fading from light and washing. The Egyptians did not know about ions, but they knew that adding certain minerals to the dye bath made the color last. In China, silk fabrics from the Han Dynasty, over 2,000 years old, retain their blue from indigo. The Chinese perfected the art of building fermentation vats to reduce indigo into a soluble form, then reoxidizing it on the fiber. That process trapped insoluble indigo crystals deep inside the silk, locking the color in place. But not every color in the ancient world was permanent. The same civilizations that produced Tyrian purple and madder red also worked with dyes that faded within months. Saffron, extracted from the stigmas of crocus flowers, gave a brilliant yellow. It was used in ancient Greece and Rome for ceremonial robes and wedding veils. But saffron yellow disappears after just a few weeks in direct sunlight. The dyers knew this. They did not use saffron on everyday garments or on textiles meant to last. They reserved it for things worn once or kept in the dark. Similarly, weld, another yellow from the Risetta luteola plant, was more stable but still required a careful mordant. If the dyer used the wrong metal or skipped the mordant entirely, the color washed out with the first rain. Ancient textile manuals, like those recorded by Pliny the Elder, list which dyes are fast and which are fugitive. They did not write in chemical terms, but they had a working classification. That classification was based on centuries of trial and error. The ability to predict which dyes would survive and which would not is itself a form of chemical understanding. The complication is this: their knowledge was empirical, not theoretical. They knew that some molecules bonded strongly and others did not. They knew that certain minerals fixed color and others ruined it. But they had no way to explain why. The gap between what they observed and what we now understand is where the true chemical puzzle lies. The chemical knowledge that ancient dyers possessed goes back much further than written records. Neanderthals, tens of thousands of years before modern humans, were collecting ochre, traveling miles to specific sources, grinding the mineral into fine powder. At sites like Maastricht Belvedere, ochre-stained tools suggest they processed pigment for hides or plant fibers. The color remains because the chemistry is simple. Ochre gets its shades from iron oxides like hematite and goethite. The bond between iron and oxygen is exceptionally strong, unaffected by ultraviolet light, water, or mild acids. An iron oxide molecule drawn on a cave wall 15,000 years ago is still chemically identical today. What is remarkable is that early humans learned to control that stability. They heated yellow ochre to around 300 degrees Celsius, driving off water and converting goethite into red hematite. This was a deliberate chemical transformation, achieved without any concept of molecular structure. They knew that fire changed the color, and they used that knowledge to produce the vivid reds of Lascaux and Altamira. That same understanding carried to textiles. Archaeologists have found Neolithic linen fragments dyed with ochre, still holding their color after 7,000 years. The foundation, the observation that certain minerals bond permanently to fiber, was already in place when the first civilizations emerged. Those iron oxides, unchanged after tens of millennia, represent the earliest chemical mastery of color. That foundation, built from ochre and fire, made the great dye traditions of antiquity possible. And among those traditions, none is more chemically surprising than the one that opens our story: Tyrian purple. The source is the murex sea snail. Hidden inside its body is a thin gland that secretes a white-yellow liquid. That liquid contains a molecule called a brominated indole, essentially a precursor not yet colored. The snail uses this secretion as a defensive irritant. But ancient dyers discovered something astonishing. If you extract that liquid, soak a cloth in it, then hang it in the sun, the cloth turns green, then blue, and finally a deep, unshakable purple. What happens in the sun is a photochemical reaction. Sunlight provides the energy to break a chemical bond in the precursor, releasing a bromine atom. This radical reaction allows two molecules to combine and form a new structure, 6,6-dibromoindigo. If you know indigo, the blue in your genes, you will recognize the shape. Tyrian purple is indigo with two bromine atoms attached, one on each ring. Those bromine atoms are the secret. Bromine is a heavy element. When sunlight hits a purple dyed fiber, the bromine atoms act like shock absorbers. They absorb the high-energy ultraviolet rays and convert that energy into harmless heat, instead of letting it break the molecule apart. This is the same reason many modern synthetic dyes use halogen atoms for light fastness. The ancient dyers could not have known about electrons or energy absorption, but they knew that this specific color, produced by this specific process, would never fade. The process itself was laborious beyond imagination. Snails were trapped, crushed, and their glands extracted. The yield was minuscule, as mentioned earlier. The scale is staggering. And the smell, by all historical accounts, was putrid. The Roman writer Pliny described the entire process as a foul trade, but the result was a dye so durable that it could be repeatedly washed, worn for a lifetime, and still pass its color down through millennia. The chemical structure also makes the pigment almost completely insoluble in water. Once the color develops, the molecules lock together in flat stacks held by strong hydrogen bonds. This stacking creates a crystal-like lattice that water cannot penetrate and microbes cannot digest. It is why that 4,000-year-old lump found in Crete still glowed purple when cracked open. Here is the concrete discovery. Tyrian purple was not just a lucky accident. It was a photochemically engineered pigment, using sunlight as a catalyst and bromine as a stabilizer. The ancient dyers had empirically discovered a process that modern chemists would not fully explain until the late 20th century. They were color artisans, yes. But they were also, in every meaningful sense, photochemists. Purple was not the only chemical achievement. Blue demanded a different kind of chemistry, and it came from a humble plant, not a sea snail. That plant was indigo. The blue pigment itself is completely insoluble in water. You cannot dissolve it, soak fiber in it, or paint with it. If you tried to dye cloth by crushing indigo leaves directly, the color would barely cling to the fabric and wash away almost instantly. The ancient dyers faced a problem. How do you turn a solid blue rock of pigment into a liquid that can penetrate cloth and then stay there forever? The answer was a chemical trick called reduction. In modern terms, reduction means adding electrons to a molecule, which changes its shape and solubility. In medieval terms, it meant a vat that never dried. The dyers would fill a large earthenware pot with water, add the crushed indigo plant material, and stir in a source of alkali, often stale urine or wood ash. Then they added fermenting bran or ripe fruit, anything that would start a bacterial feast. The bacteria consumed oxygen, creating an environment starved of air. In that low oxygen soup, the indigo molecules grabbed electrons from decomposing organic matter and transformed into a new form. Leuco-indigo is pale yellow and, crucially, soluble in water. The vat turned a murky yellow-green, and the dyer dipped a piece of cloth into it. Coming out, the fabric was almost colorless, just a pale yellow. But the moment the cloth hit the air, oxygen snatched those electrons back, and the indigo molecules reverted to their original blue form. Now they were trapped inside the fibers because the insoluble blue could no longer wash out. The cloth, pulled greenish-yellow from the vat, turned a deep permanent blue within minutes. This process, called vat dyeing, is the same one used to color denim today. Your blue jeans rely on exactly the same chemistry: a reduced indigo solution, a dip, and oxidation in the air. The ancient dyers could not explain electrons or oxidation, but they knew their vat had to stay alive. They kept it simmering for years, sometimes for generations, feeding it with more plant matter and urine. If the vat dried out or the wrong bacteria took over, the whole batch was ruined. So they guarded these vats, passed them down, and maintained a living chemical balance. Here is the practical consequence. That fermentation vat was a low-cost electrochemical reactor. It used biological reduction to solve a chemical problem that synthetic chemists would later solve with harsh reducing agents like sodium dithionite. The ancient dyers had turned a solid pigment into a soluble form, then fixed it with air, creating a color that lasts through centuries. But what about red, the deep reds that dyed the robes of Roman senators or the medieval tapestries of the Apocalypse of Angers? They came from a completely different chemical principle, one that didn't rely on the molecule being insoluble in water, but on building a tiny molecular cage around the dye. Take madder. The root of the madder plant contains a molecule called alizarin. On its own, alizarin gives a weak orangey stain that fades quickly and washes out. But ancient dyers knew that if they prepared the cloth with a metal salt first, something remarkable happened. They soaked the fabric in a solution of alum, aluminum potassium sulfate, or sometimes tin. These metal ions acted like bridges. When the alizarin molecules came into contact, they bonded to the metal, and the metal bonded to the fiber. The result was a stable, three-dimensional complex called a color lake. Once formed, that lake was almost impossible to break. The alizarin molecule was now held in a metal cage, anchored to the cotton or wool. Light couldn't easily destroy it, and water couldn't wash it out. That is why madder reds on Egyptian mummy wrappings still glow after 3,000 years. Meanwhile, in the Americas, the Aztecs were harvesting a tiny insect that lived on cactus pads. The cochineal scale bug produced carminic acid, a molecule similar in structure to alizarin. When the Spanish brought cochineal to Europe in the 16th century, European dyers quickly realized that the same mordant trick worked. With alum, cochineal gave a brilliant crimson. With tin, it became a fiery scarlet. With iron, it turned deep purple. The same insect, just a change of metal salt, and you got a whole palette of permanent colors. Mordanting wasn't limited to reds, yellows from weld, oranges from anatto, even some blues used mordants, but the principle was always the same, a metal ion that links dye to fiber. This is coordination chemistry, the same kind that gives color to gemstones like rubies and emeralds. The ancient dyers didn't know about electron shells or ligand bonds, but they had a practical rule. Certain metallic salts could fix certain colors. They experimented for centuries, building a detailed empirical knowledge, and that knowledge produced textiles whose reds still blaze after 2,000 years. That is the concrete discovery, a single chemical principle uniting plant roots and insect bodies, all harnessed through the simple act of soaking cloth in a metal bath before dipping it into color. But for all our understanding of mordants, some ancient colors still defy explanation. Take the Paracas textiles from the coast of Peru, woven around 2,000 years ago. Their reds and blues remain astonishingly vivid. We know the blue is indigo, but the red is a puzzle. The leading candidate is a dye from the rilbunium root, a relative of madder. Yet when modern dyers try to replicate the Paracas red using rilbunium, they get a different shade, more orange, less intense. Something is missing. Perhaps the ancient dyers used a specific species now extinct, or a mordant we haven't identified, or a combination of multiple plants. The point stands, we can see the result, but we cannot reproduce it. The lost secrets aren't limited to the Americas. Tyrian purple, that legendary dye from sea snails, has been recreated in lab experiments, but the precise ancient process, the exact fermentation times, the ratio of different snail species, the temperature control, was never written down. Roman dyers kept their recipes trade secrets, and when the empire fell, the knowledge largely vanished. Modern attempts produce a purple that is chemically identical, but the hue and fastness sometimes differ from the surviving fragments. Some scholars suspect the ancients used a secondary treatment, perhaps a mordant or a fixative, that we haven't figured out. These gaps remind us that even with our quantum chemistry and spectrometers, we are still reconstructing knowledge that was once routine. The ancients worked with living materials, local plants, and seasonal variations, variables that lost their context centuries ago, so the question remains open. What else did they know that we have yet to rediscover? What is actually happening at the molecular level when light hits these dyes? Why do some survive while others crumble? The answer lies in photochemistry, the study of how light interacts with matter. Ancient dyers, without knowing a single chemical formula, had engineered their colors to resist one of nature's most destructive forces: ultraviolet radiation. When ultraviolet light strikes a dye molecule, it delivers a burst of energy that can break chemical bonds, especially if oxygen is present. Oxygen steals electrons from excited molecules, creating free radicals that attack the dye structure and bleach it. Most organic dyes fall apart under strong sun. But a few molecules have built-in defenses. They absorb UV energy and safely dissipate it as heat without breaking apart. Indigo is one such molecule. Its molecular backbone is a long, flat, conjugated system with electrons delocalized across many atoms. When indigo absorbs UV light, those electrons shift into an excited state but simply relax back down, releasing the energy as vibrations the fabric absorbs as warmth. Indigo is photostable. That is why the blue in jeans, the same chemical used by the Maya and the Dyers of the Han Dynasty, can survive centuries of sunlight. Mordanted dyes work on a different principle. Madder red and cochineal crimson do not rely on a single molecule's resilience. Instead, the mordant, usually aluminum, tin, or iron, creates a tiny crystal around each dye molecule. The metal ion grabs onto the dye and the fiber simultaneously, forming a rigid, three-dimensional coordination complex. This complex physically shields the dye from oxygen and water. It also absorbs UV light and channels the energy into vibrations across the entire crystal network, spreading it out so no single bond takes the hit. That is why the reds in the Paracas textiles, which we still cannot fully replicate, have held their intensity for 2,000 years, now considered Tyrian purple. It shares the same core structure as indigo but with two bromine atoms attached. Bromine is a heavy atom. In photochemistry, heavy atoms act like a secret escape hatch. When the dye molecule absorbs UV, the heavy bromine encourages the excited electron to flip its spin, trapping the molecule in a state that cannot easily react with oxygen. Instead, the energy slowly leaks away as phosphorescence or heat. This heavy atom effect makes Tyrian purple even more resistant to fading than indigo itself. It required no modern knowledge, just the observation that the purple from certain snails lasted longer than anything else. The Phoenicians sailed from modern-day Lebanon, carrying not just Tyrian purple dye but the practical know-how. Which snails to harvest, how long to let the glands ferment, the exact moment to expose cloth to sunlight. By the Roman Empire, the recipe had reached Morocco and Greece, though the finest purple still came from Tyre. In a typical workshop there, vats bubbled with fermenting gland paste, and dyers watched the sun's angle to judge when the cloth, pulled from the vat greenish yellow, would turn the deep purple. That instinctive timing, refined over generations, could not be written down. It passed only from hand to hand. Meanwhile, Indian indigo traveled overland and by sea to Mesopotamia, Greece, and Rome. The Roman writer Vitruvius noted that Indian indigo was imported, but the fermentation vat technique remained a closely guarded secret of Indian and later Syrian craftsmen for centuries. When that knowledge finally reached medieval Europe, it revolutionized textile dyeing. The woad plant had produced only a pale blue, but Indian indigo gave a far richer, faster color. Demand skyrocketed. On the other side of the world, Chinese silk dyers mastered mordants like alum and iron salts, achieving colors European dyers would match only after the Silk Road brought alum from Chinese mines westward. Along that route, a single caravan might carry lumps of alum from the mines near Dunhuang to a dyer in Samarkand, who would test it with local madder and then pass the new recipe further. The exchange went both ways. Cochineal, a New World insect dye, entered the global palette after Columbus, but the principle of mordanting it with tin or alum had been refined in Asia and the Middle East long before. This cross-pollination sharpened the empirical science. Each culture tested new plants, new minerals, new ways to trap molecules onto fiber, but the global network also made knowledge fragile. When one empire fell, recipes could vanish from that region unless they had already been written down elsewhere or taken root in a distant workshop. Sometimes they were lost anyway. By the 19th century, synthetic dyes offered cheap, vibrant color, but early aniline dyes faded quickly. A curtain in a sunny window turned to a washed-out shadow within a season. Today, researchers run a different kind of experiment. They take fabric dyed with ancient recipes, madder, indigo, Tyrian purple, cochineal, and line them up next to strips dyed with modern commercial dyes. Then they blast all of them with concentrated UV light, compressing years of sunlight into days. The time-lapse footage is striking. The modern dyes, especially cheaper ones, crumple first. Bright reds go pink, then beige, blues turn gray, but the ancient samples hold. Indigo remains blue, madder keeps its deep, earthy red, Tyrian purple barely shifts. The experiment reveals not that all old dyes are better, but that the ones preserved in the historical record were built to last. Indigo's planar structure absorbs UV and dissipates it as harmless heat. Alizarin in madder locks into a coordination complex with aluminum ions. The bromine atoms on Tyrian purple stabilize the whole system. Those architectures took centuries of trial and error to perfect. The synthetic chemist of 1865 wanted something cheap to sell. Fading was irrelevant. The ancient dyer had no such luxury. If his color faded, his reputation faded with it. What the experiment demonstrates is a kind of chemical selection. Structurally weak dyes did not survive in the archaeological record or in the market. The ones that made it into the textiles we dig up today are the ones whose molecular design resisted the sun. So the molecular architecture of these dyes was not a stroke of luck. It was the product of generations of observation passed down from dyer to apprentice. But that chain of knowledge had a breaking point. The fall of the Western Roman Empire shattered the trade routes that kept the dyeing industry alive. Tyrian purple, which required snails from the Eastern Mediterranean and a process that took weeks, became a ghost. The last known recipe from Antiquity, written in Greek, was copied until the meaning of its steps blurred. By the early Middle Ages, no one in Europe could produce the color that had once defined imperial power. It was not just purple. The precise mordanting techniques used in Egypt and Mesopotamia, the fermentation vats for woad, the insect dyes from the Mediterranean scrublands, all of these knowledge systems relied on a network that collapsed. Local dyers still worked, but their palette shrank. Many recipes became fragmented or were guarded in monastic scriptoria where the chemistry was written down but the practical know-how faded. For centuries, European color was limited to what could be gathered in a few fields. Weld for yellow, madder for red, woad for blue. The complexity of the ancient world was a distant memory. The rediscovery began when chemistry became a systematic science. In the 18th century, chemists started to take apart natural materials and ask what they were made of. A breakthrough came in 1908 when the German chemist Paul Friedlander analyzed a lump of Tyrian purple found in Crete and identified the molecule 6,6-dibromoindigo. He proved that the ancient process was not alchemy but precise photochemistry, but it took decades to reconstruct the full extraction procedure. Even today, no one has perfectly replicated the ancient vat without modern additives. Then 20th century archaeologists turned their microscopes on the textiles themselves. Using techniques like high-performance liquid chromatography, they identified the exact dye molecules in a single thread from a Paracas mummy or a Han Dynasty robe. They found residues of mordants and traces of vat conditions. Slowly, the lost knowledge was pieced back together from chemical fingerprints. What this reveals is a humbling truth. The ancient dyers had built a working understanding of reduction, oxidation, coordination chemistry, and photostability centuries before those terms existed. Their knowledge was empirical but not primitive. When the transmission of that knowledge was broken, we did not simply lose recipes. We lost a way of thinking about color that integrated chemistry, ecology, and craft. Recovering it has taken modern science an entire century, and we are still not finished. So what does it actually take to brew colors like an ancient dyer? This is the domain of experimental archaeology, where historians, chemists, and artisans try to walk the same path, and the results are both humbling and spectacular. Take Tyrian purple. In the 1990s, a team led by the scientist Zvi Koren painstakingly recreated the process. They collected thousands of murex snails off the coast of Israel, extracted the hypobranchial gland, and placed the pulp in shallow trays under the Mediterranean sun. The snails were rare, the labor immense. They produced a few grams of purple powder, and when they ran it through a mass spectrometer, the molecule matched perfectly the ancient dye from Crete. But here's the surprise: the ancient vats would have been far more efficient. The heaps of crushed shells found at Phoenician sites suggest they used huge quantities, but also that they likely reused the same vat for months, maintaining a bacterial and chemical balance that we can only guess at. The modern team needed lab-grade reagents to stabilize the process. The ancients did not. They had a living vat culture passed down like a sourdough starter. Then there's woad. Woad is the European source of indigo, and for centuries its preparation was a stinking, alkaline vat. Modern reenactors have tried to replicate it using urine and wood ash. The results are almost always a pale, uneven blue, nothing like the deep blue of a Han Dynasty silk. It turns out that the secret is the specific strain of bacteria in the vat. In 2020, a researcher at the University of Copenhagen isolated the exact microbe that reduces indigo in a traditional Japanese Tsukumo vat. When they introduced that microbe to a woad vat, the blue came out rich and true without any modern chemicals. The ancient dyers were managing a microbial ecosystem without knowing it. What these projects reveal is not just that the old methods work, but that they require a level of practical chemistry we often overlook. The dyers had to control temperature, pH, oxygen exposure, and time, variables that only took minutes or hours to go wrong. The modern replicators succeed only when they surrender the idea that ancient was crude. They learn to think like the dyer, not the chemist, and the practical consequence is this: we now know that these processes are not lost, they can be recovered. But they demand patience, observation, and a willingness to trust the vat. The knowledge is not locked in a manuscript, it lives in the hands of anyone willing to smell the fermentation and watch the color change in the sunlight. That is a form of science that cannot be replaced by a synthetic formula. Ancient dye baths ran at ambient temperature or with gentle warmth. Indigo fermentation happened at roughly 30 degrees Celsius. Matter delivered its red without a rolling boil. Modern synthetic dyeing often requires temperatures above 100 degrees, consuming enormous energy. The ancients could not afford that fuel, so they coaxed color at low energy. That is energy efficiency by necessity, and it is exactly what a sustainable textile industry needs to rediscover. Today, some textile startups are reviving low-temperature fermentation vats, cutting energy use by half while producing stable indigo. The second principle is economy of materials. A mordant like alum or iron was used in tiny amounts, barely enough to form a monolayer of metal ions on the fiber surface. That thin coating locked the dye molecule into a coordination complex that resisted washout and sunlight. Modern dyeing often uses excess dye and chemicals to force fixation, then discharges the surplus into wastewater. The ancient approach used just enough because resources were scarce. That precision comes from generations of empirical tuning, pointing toward a chemistry of minimal waste. A few dye houses now recycle their mordant baths, recovering alum and iron for repeated use, cutting chemical runoff significantly. The third principle is the source itself. Plants, insects, minerals, all renewable and biodegradable. With the rare exception of Tyrian purple, most ancient dyes came from abundant species, often weeds or byproducts. Madder was a field weed. Woad grew in poor soil. Cochineal was farmed on cactus pads. When a garment wore out, the dyes broke down without persistent pollutants, unlike synthetic dyes that can take decades to degrade and sometimes release toxic aromatic amines. Researchers have now developed a biodegradable dye from a common plant that decomposes harmlessly in soil within weeks. These three principles, low energy, minimal reagents, renewable feedstocks, are not nostalgic. They are actionable. The hardest part is not the chemistry but the mindset. We have to stop assuming newer means better and start asking what the old methods optimized for. The answer is almost always survival, thrift, and the long view. If we combine that ancient discipline with modern analytical tools, we might design a color industry that does not trade fastness for planet. And that is exactly what a growing number of researchers and entrepreneurs are doing. The renaissance of natural color is not a fantasy. It is happening right now. Driven by a rising demand for sustainable textiles and a renewed respect for ancient craftsmanship, a wave of innovation is bringing forgotten techniques back to life, but with a modern twist. Take indigo, for example. For centuries, the only way to make denim blue was through a stinking fermentation vat. Today, biotech companies are engineering yeast and bacteria to produce the very same indigoid molecules without needing to harvest tons of plants or use the harsh chemicals that synthetic indigo requires. The result is chemically identical to the blue in a pair of vintage jeans, made in a bioreactor with a fraction of the environmental impact. The ancient chemical principle of reduction and oxidation remains the same, but the production is now clean and scalable. Meanwhile, small-scale dyers and textile mills are reviving whole ecosystems of natural color. In Japan, the ancient art of aizome, indigo dyeing from woad, is experiencing a quiet resurgence. Artisans grow the plants, ferment the leaves, and dip cloth into traditional vats, producing blues with the same light fastness as the Han Dynasty silks. In Europe, farms are cultivating madder and weld again, supplying natural dye kits to hobbyists and high-end fashion houses. The knowledge that was nearly lost during the era of synthetic dominance is being relearned through hands-on apprenticeship and careful documentation. And it is not just revival. Modern chemistry is asking new questions. Why do certain ancient textiles still hold color after millennia? Researchers are using spectroscopic analysis to map the exact molecular interactions inside a dyed fiber, discovering that ancient dyers unknowingly optimized for maximum photostability. Some of those recipes are now being studied for next-generation coatings and materials. The ancient world is no longer a museum piece. It is a laboratory that we are only beginning to decode. So, as we stand on the edge of this renaissance, the real question is not whether the chemistry works. We already know it does. The question is whether we have the patience and humility to learn from those who perfected it without ever understanding why. Ancient dyers were practical chemists. Over centuries of trial and error, they mastered the coordination chemistry of mordants to fix madder red, harnessed reduction and oxidation to make indigo soluble and then insoluble within the fiber, and stumbled upon the stabilizing effect of bromine in Tyrian purple. They did it all without a periodic table or any formal theory of atoms. Their chemical knowledge was not accidental. It was a practical science built over millennia of observation, experiment, and trade. They understood, without atomic theory, that certain metal salts could lock dye molecules into fibers, that air and bacteria could transform insoluble precursors into vibrant blues, and that a single bromine atom could make a purple that sunlight cannot fade. Their understanding of mordants, reduction oxidation, and molecular stability anticipated principles that modern chemistry would only formalize centuries later. This legacy challenges our linear view of progress. We tend to think of science as a straight line from ignorance to enlightenment, but these Dyers had already discovered the core logic of dye chemistry. They optimized for photostability and color fastness millennia before anyone knew what a photon or a molecule was. Their recipes, now analyzed with spectroscopic tools, are being studied for next-generation coatings and materials. The ancient world is no longer a museum piece. It is a laboratory that we are only beginning to decode, and that offers a blueprint for a more sustainable relationship with color, one that relies on natural sources, waste reduction, and deep empirical intelligence rather than petrochemical shortcuts. When we look at a scrap of Roman fabric or a Peruvian textile that still glows after 2,000 years, we are seeing that intelligence perfectly preserved. Which ancient dye technique astounds you the most? The snail squeezing for purple, the fermentation vats for indigo, or something else? Let me know in the comments. If you enjoyed deep dives into the hidden science behind history's greatest achievements, subscribe to join me in exploring more stories where chemistry meets the past.